Good morning, good evening, everybody. So based on your time zone, and this session is basically we'll talk about Hadoop demo part two, and what we have covered in part one is a need for Hadoop, and primarily, and at the end of the part one, we have come up with two primary uh, reasons, what are the limitations of traditional data warehousing applications and how Hadoop addresses problems. So I think I've discussed about two problems. One is storage and number two is processing. So in demo part two, basically we'll talk about how Hadoop addresses the problems of how Hadoop addresses the problems of storage and processing. Probably quickly go to the definition of Hadoop. Then probably I will explain more on a whiteboard. Then probably you can come back to the definition again. Hadoop is basically a scalable and fault-tolerant distributed system for data storage. Right, that's the problem. Number one, and processing. Yeah, it's basically this is the definition of Hadoop. We will discuss in detail how Hadoop stores the data and how it processes the data that is stored in Hadoop. And let me open MS Paint. Let's take a traditional system. Now, when you are dealing with a single machine, let's take a case. Right? Let's have a client. And let's say we have a machine. We have a this one. Let's say use this. Let's say this is a Linux machine. Let's say in a normal single machine when you are operating, we have a client and a Linux machine. If at all you want to store 640 MB file, right? Let's take this thing, writing 640 MB file. Right? And similarly, read 640 MB file. Right? Read and write. Let's see, let me put the size of the file as well. 640 MB file. Sorry, yeah, 640 MB file. So when you are writing, probably all the 640 MB of a file is stored in single machine. Everything will be stored here. When reading also, it has to read entire contents of the file, 640 MB file, and return it back to the client. This is basically straightforward. That is how it works when you are in your in your single desktop, when you are writing the file and reading the file. When you write it, all the contents of the file, in this case 640 MB file, is stored in your disk, and while reading, it has to read all the 640 MB file, and all the operation is done by a single machine. So that is how it works in case of a single machine. And we'll talk about Hadoop. I think you have already given introduction of Hadoop. It's basically uh, it uses a cluster. Right? Cluster is a set of machines. Now all the distributed storage and processing will happen in a cluster of commodity hardware. Right? So unlike in a traditional system, database system, where you have one machine, a powerful machine, enterprise-wide um, a machine, which is probably used in RAM and many cores, probably 8 cores, and probably 640 GB RAM, whatever. So huge machine, but Hadoop works in a cluster of commodity hardware, right? I think we already talk about the cluster. Cluster is basically a you have a rack here. Rack has a stack of computers, and Hadoop works in a cluster of commodity hardware. So let's go back here. Same example client call. Let's say we call it Hadoop HDL Hadoop client. As it operates in a cluster, let me draw more machines here. I think the easiest thing would be okay, let me draw this diagram. Probably it's worth understanding in detail. Let's say we have here Hadoop uses master slave architecture. Let's say we have this machine. Let's say let me call this as enterprise hardware. This is basically a master, and below everything is slaves. Right? So, and as I mentioned again, probably mentioning it again, Hadoop uses a master-slave architecture, and in this case, we have a master. Let's say it's a single machine. Let me call this box as master 1. The machine name is, let me call it M1. Right? This is the one machine, right? And let me call these things as node 1, node 2. Right? This is node 1, node 2. Node 4, node 6, 7, node 8. Yeah, so on and so forth. So we have a 12 node cluster. Assume that we have 12 nodes and make it very simple. We have a one master node M1, right? And when you try to save a file, same example, 640 MB file, again size is same, write 640 MB file, read 640 MB file. So unlike in here where everything is written to a single machine, and when you are reading, all the 640 MB of the file will be read from the single machine. So all the work is done by a single machine in this case. So in case of Hadoop, it works like this. When you try to save 640 MB file, it's physically split the file of size either 64 MB or 128 MB. So, for our convenience, here we will take the size of the block is 64 MB. So, when you try to save a file of 640 MB, it will split into, let's say, the size is, as I mentioned, 64. So, it will split the file into, very simple, right? Our size of the file is 640. So, I have taken probably the numbers which gives an easy number basically. Let's say 640. The size is 64 MB. That is the reason I have taken a 640 MB file. Right? 10. So it will split into 10 blocks. Right? Because our size of the block is 650. Right? This is a configured. Right? Usual size is 64 MB or a 128 MB. And when you are trying to save a 640 MB file, it will split into 640 divided by 64. We have 10 blocks. Right? What we have is 10 blocks. So I will repeat it again. When you are trying to write a 640 MB file, it physically split the file. Now the original file is 640 MB file. It physically split the file into a small chunks. Right? The size of the each block is 64 MB. So we get 640 divided by 64. We will get 10 blocks. Right? And what the master stores, master doesn't store any data. What master stores is basically metadata. Metadata is basically data about data, right? Master is basically it's a file system. What it stores is we have 10 blocks. I'm calling the blocks as block 1, 2, 3 until block 10, right? And what master stores is where each block is storing, right? I'm giving the names N1 and 2 as the name nodes. let's say N1 is storing block 1, right? N2 is storing block 2, so on and so forth. Here again I'm making it very simple, so giving the same assuming here node 1 is storing block 1, node 2 is storing block 2, etc. And node 10 is storing block 10. We have 10 blocks and each node is storing one block of information. Let's say the size of the file is 680 MB file. What you have is 11 blocks, right? First 10 blocks will be of size 64, and our total size is 680 MB. So 680 minus 640, whatever, that is a 40 MB will be the last block, right? It need not be 640. Your file can be 680. In that case, the size of the last block will be 40 MB. Right? So here, what I'm saying here is block 1. I'm storing block 1 here. Block 1, block 2, okay. Block 3, block 4, let's say until block 10. Okay. 10. Here, let me name it fast. This also node 9 and node 10. Right? So now the slaves are the one which are doing the actual storage, and the master doesn't store any data. What it basically stores the metadata. So where each block is stored across the cluster of nodes. We have a cluster of 12 data nodes. What we call it, or what these slave nodes are called, data nodes, right? And where each block is stored, it will be stored by the master. Right? All these are connected. Right? We connect everything. Simply connect it. It's a basically a cluster. Right? And all these, let me put it a big this thing here, that all are connected like this. Because all these nodes will also talk to master. I am talking to this master as well. So all machines are connected. It's difficult here. Let me draw one this thing so that all are connected. All the nodes are connected. Right? So when you are trying to store 640 MB file, it physically split the file into a blocks, 10 blocks, and the master will store where each block of the file, total file, is stored. That information is stored by the master, and the slaves will store the actual data, in this case block 1, block 2, block 3, block 4, block 5, block 6, and so on and so forth until block 10. Right? And this master is enterprise level hardware, so probably the size of the RAM is much more than what the slave nodes, and even the number of CPUs, number of cores is much higher than the slaves. So sleeves, it can be a commodity hardware. Commodity hardware is basically what you and me use as a personal desktops. So these, whatever the below the line, all these can be a commodity hardware. Let me put it here. And this machine is master node M1. M1 is basically enterprise machine configuration. Right? So this master will store the metadata, and the actual data is stored in the slave nodes. So that's basically writing the file. When I'm reading the file, right, I cannot ask directly to the node for and give me the file. It doesn't know where all the blocks of the files are stored. So basically, when you are reading the file, we have to go to the master node, and you have to say, give me the file. Right? Give me my file. Let's call the name of the file is F1. Give me the file F1. So what it does is it knows what the file as contains. In this case, the file 1, let's say we call a file 1 has 10 blocks from block 1 to block 10. So it knows this file 1 has block 1 to block 10, and these blocks are stored in N1, N2, so on and so forth. So the master talks to the slaves, what you call it data nodes, and asks for the small chunk of the file, which is a block 1 for the each node. So node 1 gets the block 1 of the file, node 2 gets the block 2, node 3 gets block 3, node 4 gets block 4, and all these will happen in parallel, right, when you are processing. So we get the information from each node, block 1, block 2, block 3, get all the block information. When you have all the blocks from block 1 to block 10, it will merge and give it back to the client. So unlike in this machine, right, unlike in a single machine where the IO, where IO is basically IO is 640 MB file, total IO is 640 MB, 640 MB, right, by single machine. Leave it, single machine, right, single machine. In this case, what we are doing is, though we are reading 640 MB file, right, we are given to 10 different nodes, and each node IO is just 664 MB. So all these IO reading will happen in parallel. So basically now we are dealing with only 1/10 of the file, right? Each node is doing the IO in parallel. So you get the linear scalability. Now all N1, N2, N3 all will read the file only 64 MB and will merge it and return it back to the client. So here it's very scalable, because unlike in this machine where we are reading a 640 MB file, here we are reading a just 640, 64 MB by a single node. Right? So that's basically a read. Right? So that's how the write and read will work in case of Hadoop. Right? But as we mentioned here, I know this is a commodity hardware. This is not. It's not a problem. There's a problem here, because what you're saying, it's a commodity hardware, not an enterprise machine. as in case of master, and also usually in a single machine servers, but these name node, so data nodes, this runs on a cluster of commodity hardware. So when you are dealing with a commodity hardware failures are pretty common, right? And if one of the node goes down, right? Let's say the node 2 has gone down. So when the client requests for a file, right, and it knows node 2 contains block 2, right, to serve the client back, we have to get all the blocks from block 1 to block 10 to serve the client request. But in this case, as block 2 is down, right, as this guy is down, right, as this one is down, node 2 probably due to hardware failure, let the node 2 is down. So we cannot get the block 2 information. So we cannot serve the client request because we cannot do partially. We have to get all the information to serve the entire file, which is a file consisting of block 1 to block 10. So I mean, so what Hadoop does to make it reliable storage, right? Without, if you have just one copy, it's not reliable because one of the node goes down, we cannot serve the client request. So it has something like a replication factor, right? Let's say RF. So default is 3. Default value is 3. Again, it can be configured, right? You can change the replication factor at a fine level as well. What it basically replication factor is 3. What exactly it means by this? Let's say I am already node 1 is already stored in block 1, so it also stores 2 more copies of the file. What it does is block 1 here, and let's say block 1 here. Similarly, block 2 also it will be stored here and here. What? So, as we discussed before, if this node goes down, it's not at all a problem because now we have more than one copy of the block. Right? It goes to the node 8 and gets the block 2 information and give the data back to the client. So, because of replication factor, we have increased the reliability. Right? It's reliable now, right? Before it's not reliable because one of the node goes down, we are not able to serve the client request, right? And probably you might ask questions like, because of this replication factor is equal to 3, let's say we have a data of, simple example, 1 terabyte, we ended up storing 3 terabytes, right? Because we have 3 copies of the data, right? We have 3 times the original size of the data. But still, it's not a problem because let's say we have 100 machines. Let's say I'm going to go to 100 level. Let's say we have 30 nodes. No, we have 30 node cluster, right? We are getting the capacity of 30 machines, 30 different nodes, but we are storing only 3 times more than the actual data. So, but because when you are dealing with a cluster of probably 30-40 machines, replication factor 3 is not a problem, right? That's one thing, right? And apart from this, this replication factor also helps in improving the performance. Let's say, example, this client 1 is requesting the same file 1, right? When it's serving the client request, client 1, somebody else also requested the same file, client 2, same file F1, right? For serving the client request 1, probably node 2 is getting the data from B2, right? it's busy serving the client 1. So client 2, when it's getting the information, probably it will assign the task to node 8 to serve to get the B2 request, because this node is busy serving the client 1 request. For client 2, it gets the data from a different node which holds this data, right? And this redundancy is also helps in improving the performance of your read as well. And apart from that, it's more reliable now, because even one of the node goes down, but still we can serve the request because of other copy of the data, right? That's how Hadoop, stores the data, right? Now here, how HDFS is called. Basically, this is called, all this is called HDFS. Hadoop Distributed File System. Why you are calling distributed? Because your file is not stored in a single machine, unlike traditional servers. Your file is distributed across different machines in the cluster. Right? In this case, your file is stored in 10 different machines. Node 1, node 2 is nothing but a machine. That is why it's called a distributed file system. Right? And again, it uses the master slave architecture, master as a metadata, and the slave stores the actual data. So now when you discuss about the problem number one, it's a storage problem. Here it's easily scalable. This is called horizontal scalability. Let's say when you are running out of storage space, just add one more node. Right? You keep adding nodes. Just I want to make it big, small only, right? So it's easily scalable, and if you are running out of space in your cluster, just keep adding node 1, node 2, node 3, node 4, whatever, extra nodes. I think we have already node 12, let's say. You keep adding node 13, node 14, node 15, node 16. So it's highly scalable storage, unlike in a single machine where it's difficult to increase your disk space after a certain point of time. It's difficult to scale in storage, but here no problem, just adding more nodes, keep adding the nodes to store huge volumes of data, right? That is how Hadoop addresses the problem of storage, right? Basically, it uses HDFS, Hadoop Distributed File System, to scale storage. Okay. How it scales? Okay. Adding more nodes. Yeah, I think this is how the storage problem is addressed in Hadoop using HDFS. Right? This basically uses horizontal scalability. In data warehousing world, usually called scale out architecture. Yeah, and but when I go to processing, right, um, right, and we have talked about what we have talked about so far is storage, right? This master main as storage, one part is storage, right? Let's say called storage. We have discussed about storage so far, right? Storage, how it stores the file, everything, right? And for processing, similarly, we have for processing as well. Let me highlight some of the things, which I think is very useful. Control Z. Let me this This is storage. First thing is storage. We have covered storage, right? And other is processing. Let me make it more processing. Just I want to let me find those. Yeah, processing, and here let me highlight this one as well, because these are the two important problems you have to address, and this is what talk about, right? Storage, I think we all discussed. We'll talk about now processing part. Let me give better color. Right, this is processing. And processing, probably I think it might be easy to take a practical example, right? Storage is pretty clear because it's physically split into a block, and each block is stored. When you are reading, it will be assigned to each node, get it back, and serve the client request, right? So we are reducing IO in case of by reading the file to just 64 MB by each node. IO 64 MB. That is how we 64 MB, right? And that's clear. I think it's very clear. Post always, I think you have spent significant amount of time. So processing, probably, I think as I mentioned, we will take a real-time example. Probably that is easy for me to explain. Let's assume that, right, we have 10 students, right? Not like that, probably. Let's say I'm the master, right? Similarly, this is the instructor, right? Master is nothing but an instructor, right? For processing, let's say I am the instructor, and each node, probably in a practical scenario, consider the student. So I am the master, I have 12 students with me, right? Assume that let's say I have 10 pages, right? I have 10 pages, and all 10 pages basically as example, maximum temperature, not maximum temperature, temperatures recorded in India in last 5 years, right? Let's say, again, let me repeat, I have 10 pages with me, normal pages. The data the pages contains is basically temperatures recorded in India across different cities in last 5 years. And again, to this thing, let's say here assume that, what here practical scenario, assume that this block 1 is page 1. Assume that this is enough. Just to make it simple, block 3 is page 3, right? What I'm saying is a block, right? Yeah, and block 4 is page 4, so on and so forth, right? So now my requirement is, my processing requirement is, I hope it's clear, right? My file is nothing but all 10 pages, right? While storing, what Hadoop does is each block it splits into 64 MB, so its storage is finished, right? While processing, to compare with the real-time example, I am giving an example of what you call, let's say block 1 is nothing but a page 1, right? I have 10 pages. Now my requirement, processing requirement is, I want to get the maximum temperature ever recorded in India, right? You have 10 pages, go to the 10 pages and figure it out, the maximum temperature ever recorded in India. Right? If the same requirement is here, because all 10 pages are stored here, which is nothing but 640 MB file, what it does is it scans all the 10 pages and gives the maximum temperature ever recorded in India. But in this case, in Hadoop world, because I have 12 students with me, what I do is I will give each student one page. I will give each student is nothing but my node. This node can be, right? In a practical example, this node can be as student 1. This node 3 can be in real-time analogy, you can take it as student 3, right? And these are my slaves who does the actual work, in this case processing. So what I've done is, for student 1 I have given a page 1, student 2 page 2, student 3 page 3, right? So on and so forth. So for all 10 students I have given one page each, right? I am the master who is controlling everything, right? Now, so as my requirement is maximum temperature ever recorded in India, which is there in all 10 pages, as I have not given all 10 pages to one student, what I will ask? Basically, I will ask him, each student, give me maximum temperature recorded in your page, right? I will say, student S1, give me maximum temperature recorded in page P1, nothing but your file, right? And this is, yeah, I mean, this is basically, yeah, that's basically what I get is, from each student, I will get maximum temperature recorded within his page. So processing, it will Hadoop uses MapReduce, right? Right? This is called processing. Let me give this processing. It uses MapReduce. Right? Let me link these two just to understand. Right? Storage, I think we've already discussed. It uses HDFS. Sorry. Let me give this to HDFS, right? And this one. Storage is HDFS. Oh, sorry. Covered. This one. Storage HDFS, processing is mapping. So what we have discussed so far, giving each student just one page and asking the student, give me the maximum temperature within each page, right? So MapReduce basically has two phases. Basically a mapper function and a reducer function. So this is nothing but a mapper function, right? What I'm asking each student to give the maximum temperature within his space is called a mapper function. Right? So all 10 students will do processing, in this case finding the maximum temperature within his space, they will do in parallel. So for one student scanning the entire 10 pages, if it is taking 10 minutes, for each student just scanning the one page, it will take 1 minute, right? So that's the processing power of Hadoop. So we are almost getting linear scalability. What is taking around 10 minutes in a single machine, we are getting it done in just 1 minute because each student is scanning only one page rather all 10 pages, right? My end goal is not completed. My end objective is basically to get the maximum temperature ever recorded in India. So what I get is I will get the output from mappers, right? Oh, I got the output. My output is each student gave me one output, maximum temperature recorded in his base, right? Now I got all the 10 outputs. Now what I do is I will give it to one more node, let's say, because we have not used node 11, we will use node 11, right? Again I will give node 11, which is nothing but a student 11. I will give all the 10 temperatures recorded in each page, maximum temperature recorded in each page, and give it to student number 11 and get me the maximum temperature ever recorded. Right? Again, I am the master. I got the output from each student. I will give to another student, 11th student. What the 11th student does, just go through all the 10 outputs given by each student and he will come up with maximum temperature ever recorded in India, right? And here that is called a reducer function, right? And mapper is basically in this case giving maximum temperature in a page, right? So reducer, what it does is, right, scan through max temperature from page 1 to page 10, right? Scan through maximum temperature in page 1 to page 10 and give output of max temperature ever recorded, right? Right, recorded. So here this reducer function depends on mapper output, depends on mapper output, right? Unless I know the maximum temperature in each page, I cannot calculate the reducer function, right? So mappers will run in parallel, as I mentioned, as I'm giving to each student. So mappers will run in parallel. You get linear scalability. Probably what can be done in 10 minutes, you are able to do it only in 1 minute. So that is how MapReduce works, right? Because reducer function is not very complex in this case. It will be done pretty fast. Now just go through 10 records and give the maximum temperature. And the primary workload here is going through the map phase, scanning through the entire phase, which is done by 10 different students, unlike a single student in a traditional machine. So we will get linear scalability, and that's the power of MapReduce. It's basically divide and rule, right? I am not scanning the all 10 pages. I am scanning only one page that is assigned to a node 1 in my cluster, and once I get the output, I will basically calculate the maximum temperature by starting one more function which is called reducer function, which depends on mapper output. Right? And one more thing we have to note here is whatever the task I am assigning to each node or each student is independent of other task given to student 2, right? That is how we can achieve parallelism. Let's say if student 1 some reason is not able to scan and give me the output, just I will assign to 11th student to scan and give it back. And it is no way impacting the student 3 in scanning the page 3. So these are independent tasks, right? That's also important here. The mapper tasks are independent tasks. Even if one of the node goes down, then probably you can assign to some other node. And one more important thing here is in MapReduce is what you call is, right, computation will go to data, unlike the traditional systems where data comes to the computation. So example here is, right, when I am giving a task to student 1, yeah, in this case let's say at node 1, I will ask to process the data on B1. So because node 1 is having the block 1 data, there is no network traffic involved. So it need not talk to any other node to compute what is the maximum temperature recorded within the block 1. So node 1 is here, even block 1 is also here in the same machine. Block 1 is stored in node 1. So I will assign the task to node 1, give me the maximum temperature within B1. That is how now we are sending the processing computation to the node where data resides. It's called data locality. There's no network traffic involved in case of mapper function usually, right? Because it will ensure that it will give to node 1, process the data on block 1, right? In most of the cases, it doesn't assign work to the node 1 to get the data or to process the data of block 2, right? That is how it works in the traditional systems. So data locality is most important thing in MapReduce. Because of data locality, there is no network traffic involved. No network traffic. No network traffic. Network traffic. Right? And this is a very costly thing, moving the data from node 1 to node 2, node 2 to node 3. This is very costly thing. Probably we will avoid this because we will ensure that we will give the node 1 task of processing the data in B1 where the data resides. Right? This is called computation. My processing will go to where data resides. So that's the probably key features of MapReduce. One is it has a mapper and reducer function, and the other thing is MapReduce processing will go to, or a computation or processing will go to node where data resides. So basically there is no network traffic involved. Yeah, but once the mapper emits the output, then there will be network traffic, right? Because all my output is stored and it's given to the reducer to compute the maximum temperature. So that is only place where you have network traffic involved, but that's usually not a huge volume of data, unlike processing the complete block of the data. So each mapper output get it, and then we have a network traffic involved, and we will give to one other node, right? Let's say node 11 give the reduce task. So as the data from node 1 has to come here, just 1 minute. So to get the data, node 1, node 2, node 3. This is only place where network traffic is involved. Otherwise, whole processing in this case, operating on block 1, I've given the task to N1, so it does all the processing here. We need not talk to node 2 to get some data in some other machine and process it. So this reduces the network traffic, and this is the one of the key benefit of MapReduce program. So yeah, I mean that's about Hadoop, storage and processing. And processing is, right, as you mentioned, you are able to probably as I mentioned here, 10 student, one student getting X temperature in 10 minutes. We're able to get it done. 10 students process, scan, one page, get it done in almost 1 minute. That here 10 pages, because I'm giving all 10 pages to one student. That is how it works in traditional systems. This is how it works in case of Hadoop, right? And the one more important thing is, if the size of the file is growing, still we can get the things done in 1 minute. Let's say we have a 20 node cluster, right? Size of the file is 120 as 1280 MB, because let's say you have taken 640 MB file, right? That's what we were talking about, example 640 MB file. I've increased my size to 1280, right? And probably if it's taking 10 minutes, right? Let's say 640 MB file, 10 pages, right? Practical example, 10 pages. At 128 MB file, it will become 20 pages, right? If I give to all 20 pages to one student, it will take 20 minutes, right? In Hadoop, if we have, let's say, 20 node cluster, 20 students, our practical example, just giving analogy of one node, one cluster, one node is one student. I will give again only one page to each student, and they will get me the things in 1 minute only, right? So 20 minutes in case of a single machine, still you'll get it things done in 1 minute if you have 20 students. That's the power of Hadoop MapReduce. If your application is not scaling, add one more student, right? Is nothing but add one more node. So still you get the things done in 1 minute, right? I hope it's clear. And that's how storage and processing problem is resolved in Hadoop. Storage using HDFS and processing using MapReduce. What? Okay, now go to the definition. Scalable. Why scalable? Keep adding more nodes, right, to make it more scalable, right? As I mentioned, If you are 20 students, even 20 pages will be get done in 1 minute. Fault tolerant, because we have more than one replica of data, even one of the node goes down, but still you can serve the client request. Distributed system for data storage, that's what I talked about it. Your file will be split and stored in 10 different machines, 20 different machines across the cluster. So your data is distributed, and even processing also distributed, that I'm giving each node in our analogy each student to get things done. So we are doing these things, distributed storage and processing. Yeah. Probably in later classes we will go in detail. I think at the moment I think you got clear picture of how HDFS stores data and how MapReduce processes the data. Yeah, Hadoop key characteristics, scalable, right? If you don't have enough storage, keep adding nodes. If you're not able to process the data, keep adding more nodes. You need not change any code, just adding more nodes will make it scalable. It's a horizontal scalability, right? And it's reliable because we have more than one copy. Even one of the node goes down, still you are able to serve the client request. And economical, because as I mentioned, these slave nodes runs on a cluster of commodity hardware, so which is economical compared to buying one very large machine with huge processing power and storage. And flexible because it can store any kind of data. It can be a document, it can be a file, it can be a binary file, any kind of data, structured, semi-structured, uh, all the data can be unstructured data can be stored in Hadoop. So the key characteristics: scalability, flexibility, economical, and reliability. And that's what I've discussed. Probably can go through this slide later. Right? Yeah, and let me go to this again. Right? You called storage and processing HDFS, right? And the master for this is called, again we will go in detail later, this is called a name node, right? Storage is handled by called name node. Again I will connect this guy with this so that I think you can understand, right? This is called a daemon, right, which handles all the storage part, right? So name node basically stores all this information where block data is stored in the slave node. So Hadoop basically has two things: storage will be done in HDFS, and the daemon that is responsible for the complete storage is called a name node. Similarly for processing, right? This is the master, and this is called daemon is called resource manager. Right? This is RM, right? So this is processing taken care by MapReduce, and the daemon is called a resource manager, right? And here, right, we talked about one is a storage part, right? Storage, there are two things. One is the storage. First, how to store this data, block one, that will be handled by data node. Data node. This is called name node, which doesn't store any data. What it stores is the where the block is stored, which machine, which node, and actual storage will be done by, this is called a name data node, the storage part of Hadoop service. Now data node daemon is responsible for storing the block 1, block 2, block 3 information data node. Right? This is storage. Similarly for processing, right? This is called resource manager, and this is called task manager, right? This daemon is called task manager. Let me put a task manager and we put TM, just TM, task manager, right? As I said, MapReduce, this task manager is responsible. Usually when give the task, it will give nothing but a student, right? Kind of student. It gives task of processing the data in basics, right? And the service responsible for processing is called task manager, and the service responsible for storing the data is called data node, right? And these are different services, and we teaches a master slave architecture. There are two masters, one for the storage and one for the processing. Storage HDFS, and the service responsible for it is called name node. For processing, taken care by MapReduce, and the service responsible for processing the data for the master part is called a resource manager. And the slaves actual block information, storing the block information, this will be handled by a data node service, and processing actual tasks that is doing. Example is scanning through the block of this data and getting the maximum temperature within this block. This is taken care by a task manager service, right? And each and every node, right, data node and task manager coexist. So every most important thing is every node has, let's say, data node, let me call data node, and is called task manager. Every node has a data node and task manager, right? And data node is responsible for storing the data, task manager is responsible for um, processing the data within this node, what it is storing. So that is why this processing will happen usually on this data only. So both are running in the same machine, with no traffic involved. This task manager is working on a data blockade which is stored by data node. So that's, I think, all discussed data locality. So each and every slave node, we have two processes, data node which is responsible for storing block data, block 1, block 2. For processing is the task manager which operates on this data stored in this node. That is how we achieve the data locality, the no transfer traffic involved, right? Right? And I think it is a master slave architecture. Master is resource manager, and right, sorry, this is something, sorry. Okay. Right, this is node manager, sorry, right? I think confused with task tracker. Now it's basically node manager, right? Let me erase this. Right? This is called a node manager. Right? Node manager, sorry. Yeah? Node manager. This is also a node manager. Right? Sorry for this. Yeah, and node manager is which does the actual processing. This is called a node manager service. Yeah, let's go back to this thing. That node manager is responsible for these slave nodes, and this is the better place because each node has a node manager, but master is only one service, right? Name node and resource manager, but data node and node manager will run in each and every machine in the cluster, basically the slaves, right? We'll talk about later what is a secondary name node, right? Data node is a slave, name node is a master, resource manager master, node manager is a slave for processing, slave for storage, and this will be stored in each and every machine in the cluster, as I explained here. Right? Node manager data node. No, all machines. Yeah. I hope it's clear. Yeah, and this is already discussed. What you have is a replication factor. When you are storing a file, let's say it's split into blocks, and these blocks will be stored across different nodes in the cluster, which is taken care by data node for storage part, data node, data node, data node. We have basically a replication factor as well, more than one copy, right? And I think I've already discussed in detail. So probably let me quickly go through it. Right here, so one machine is taking 43 minutes. We have a 10 machines, right? Because IO, because data is distributed across 10 machines, right? We will get things done in 1/10 of the time, right? So that's the power of Hadoop. That's what I've discussed so far. Now, one student, 10 students, even while reading as well as processing, because while processing, I need not process the entire file, right? And here, probably when you talk more, probably we'll discuss more about MapReduce processing in detail. But in this case, what I've covered is, let's say we have 10 pages. What I've discussed is a 10 pages, right? I'm giving each student a map a task. Map a task is nothing but maximum temperature within that page. Assume that this split is nothing but page, and this map one is nothing but a student. In this case, what this split of the file is nothing but a block of the data. Actual processing is nothing but done by a within a node manager. One task will start. That is nothing but a student counting, getting the maximum temperature within the page, right? Here in this we call a block of data within the page, and the processing is done by node manager. Actual task will be done by node manager to scan the page and get the maximum temperature. This is called the mapper, right? This is mapper. Let me put more probably. That's a mapper 1, it's a mapper 2, mapper 3, mapper 4, mapper 5, so on and so forth. So mapper 4 is operating on a block of data and give me the maximum temperature within this block, which is nothing but probably when you talk about analogy of a student within a page. So once all this is done, this reducer is the one which gives the maximum temperature ever recorded. So here also the same thing, reducer. We'll talk about later. Here there are multiple reducers, but in this case our requirement only one reducer is good enough. We'll talk about this in the later sessions in detail, why there are multiple reducers here. But in this case only one reducer. Each mapper will give the output, and I will start a one more reduce task by this node manager, right? And it gives the maximum temperature ever recorded in India. Right? Again, it's a horizontal scalability, that we need not change code, we need not change the how you structure your data. Now, without doing any changes, right? We can increase the scalability just by adding more nodes, right? And Hadoop is widely used in now different domains. I think Visa is using, Visa is basically payment systems. Probably whatever cards you will use, majority of payment systems are Visa and Master, and they're using it for some faulty transactions, right? If your credit card is stolen, somebody is doing transactions, based on the purchase pattern, they will be able to figure it out whether is the uh, original customer doing the transactions. They're using big data, which cannot be done with the traditional systems. They're able to do it with Hadoop, because you have a huge processing and storage capacity. That's what you've covered so far, right? Hadoop adoptions, Visa and JP Morgan says, again they're using for probably you can read this thing, right? And JP Morgan is also using for fraud detections. Um, just to give a quick example, let's say, right, how the fraud will happen is probably if somebody is transferring you 10 million data, right? They can easily figure it out that probably this is something. It might be a fraud transaction, and they will call you, whether this is the right transaction, how you got the money, what the source of money, and all those things. So usually what these guys will do is they don't do in single transaction. Probably they will do multiple transactions with a small amount, right? Even there is an algorithms which goes through these transactions and figure it out whether it's a fraud transaction or not. So again, for this, they're using Hadoop, right, in financial systems. Yeah, in telecom, uh, it's also get the insights of the customers, and for controlling the churn. Churn is basically moving from one operator to other operator. So basically, Hadoop is used uh, to get the. Yeah. So, main as Hadoop is flexible, probably they can store structured, unstructured data, and probably they have algorithms using which they're able to figure it out the insights of the customer behavior, and they're able to control churn of customers in telecom domain, using Hadoop. Yeah, and so Aadhaar also using Hadoop, right? I mean, they have many technologies. They have Hadoop, they have Solar, they have MongoDB cluster, and because Aadhaar is um, citizen's identity card. It's more like a citizen identity card. We have huge volumes of data because it's not just a structured data. We have like fingerprints, iris, which has huge size, and to store all this data, huge volumes of data. It's using Hadoop for the data storage, and even for reporting using Solar and other technologies. Right. So we will talk in detail when you go to the project. What are different use cases, and what are different technologies using which you can create a big data projects. And but as of now, so most of the domains they start using big data Hadoop to get the insights of the data for making better decisions, not to improve the market share, to compete with other peers in the market. Yeah, that's basically adoption. I've seen it in telecom. You can see it payment systems, financial, um, even Aadhaar, and and even Yahoo. They store a huge volume of data. I think we need not discuss about that. Facebook, Yahoo, Google. Google, they have their own this thing. Of course, it's inspired by Google file system only, right? And yeah, Yahoo, and everybody use Hadoop and big data. Now, basically, some questions now. So, what file system does Hadoop uses? Yeah, it's basically HDFS, right? And how to process data in Hadoop file system? The processing will be done using a MapReduce. There are two phases, mapper and reducer. I think we have discussed in detail. Yeah, probably again you can go to the video if it's not clear. So what are four key characteristics of Hadoop? And this is reliability, economical, scalable, flexible, right? That's the main characteristics of Hadoop. So Hadoop ecosystem components, Hadoop as a framework, it's not designed for just for writing Java programs using MapReduce for processing, because there are other non-Java programmers as well who who are proficient in SQL. They want to analyze the data in Hadoop. So Hadoop framework has other ecosystem components for non-Java programmers. I think we've already discussed in detail about HDFS. These are the two core components within Hadoop ecosystem. HDFS, MapReduce. Probably we'll discuss more what is yarn. That is already covered. Flume is basically a data integration tool, and we will use Flume in case of a streaming data. So before we start analyzing the data, we have to get the data from external systems and store it in Hadoop. So for streaming data, basically we will use Flume to get the data into HDFS. Again, Scoop is used for data integration. Flume basically used for streaming data, and Scoop is when your sources are relational databases like MS SQL Server, MySQL, Oracle, to integrate the data from RDBMS into uh, Hadoop, we will use Scoop. It's also basically a data integration tool. Other thing is a pig. A pig basically, again, it's a pig is an ETL kind of data flow language, right? And this is developed by Yahoo because I think we have discussed in detail. We use a MapReduce to process the data stored in Hadoop. So not everybody, usually you let a MapReduce programs in Java. We cannot ask some business analyst who knows SQL to get proficient in Java and write MapReduce programs to, to analyze the data in HDFS. So what they have done is Yahoo, they have written a language called Pig Latin, and Pig is basically high level language on top of MapReduce. So we will write the code as a developer in Pig Latin scripts. This will be internally converted into MapReduce program and analyze the data. For developers, anyhow, it's pretty easy. What he writes is a Pig Latin language, which is very easy and you can learn within less than a week, unlike writing a MapReduce programs in Java. So they've developed Pig, right? Um, and HBase is a NoSQL column-oriented database for Hadoop. And the need for HBase is basically for random access. And we will talk in detail basically in the later classes. We have one complete session, in fact more than one session for HBase. We'll talk about different NoSQL databases and HBase. Right? It's basically a database within Hadoop ecosystem. Hive, yeah, Hive is basically a declarative language. Declarative in the sense it's similar to SQL, right? We don't, unlike in a pig, which is a data flow language where you can write multiple steps to get what you want. In case of Hive, you will write just single statement. See, can sign a single cell statement. It's a declarative language and it's similar to SQL, right? HiveQL, what you call is a HiveQL, and it's similar to SQL. And this is developed by Facebook. Again, the reason is same. We cannot ask business analysts to learn Java and write MapReduce programs. Just they are familiar with SQL, and HiveQL also similar to SQL, and they will write just a SQL statements. And again, this is a high level language on top of MapReduce. And when you write a HiveQL statement, it will be internally converted into MapReduce program, which does the actual processing. Right? Uzi is basically, yeah, it's a scheduling tool to schedule our jobs, whatever the ETL jobs everything you will write it, and you have to schedule it because it's not possible to run the jobs manually. You might be having 100, 200, 300 job, 300 process you have to run, which cannot be handled manually. So we will schedule everything using Uzi. And Mahout is data science. It's you have stats, data mining algorithms, everything within Hadoop ecosystem, a Hadoop framework. And again, probably what I've discussed, the different ecosystem components, you will see it in a architecture diagram. So that's probably answers if you have any questions. As we discussed, Flume is basically used for semi-structured and unstructured data. This is a data integration tool. We will data from external systems into Hadoop for streaming data using Flume. Right? Scoop structured data like database, Excel files, right? To bring the data into HDFS and even other way around as well to get the data out of an Hadoop HDFS to a relational database, right? And we've discussed about MapReduce and Hive. It's a declarative language. It's similar to SQL, HiveQL. We will write HiveQL statements to process the data within HDFS. Similarly, Pig Latin, what we will write Pig Latin scripts, and it's again a high-level language on top of MapReduce. It will use to process the data for data analytics, basically for to get the meaningful information out of data stored in HDFS. You can use a Pig Latin, and it is a data flow language. We'll talk about in detail other things. Probably we'll talk about Hadoop 2.0 and HBase database. Again, it sits on top of HDFS, and it's a NoSQL columnar database for within Hadoop. And Uzi is basically, as I mentioned, we cannot run all these jobs, whatever the jobs, start from data integration and some analysis, data cleansing, transformations. We cannot run these jobs, so we use usually Uzi to schedule the jobs. Probably in other data warehousing systems, I think most widely used is Autosys, to schedule the jobs. Yeah, yeah, I think market is for Hadoop. I think we need not discuss much. I think this is the probably so Hadoop big data is a buzzword everywhere. There are a lot of opportunities, and most of the products are still in evaluation phase, and probably they slowly move to piloting and production, and it increases the job opportunities significantly. I think no, yeah, I mean it's compared to other jobs, it's also highly paid. Definitely will be paid probably 20% more than what other technologies. Yeah, I mean this is definitely good area to learn Hadoop and big data. Yeah, yeah, that's it. I hope you enjoyed the session, and yeah, probably um, we will share our telephone numbers and probably email IDs. If you are interested, probably please reach us. Our number is basically mobile numbers. Yeah, please reach us on these mobile numbers. Um, Venkat, and next was my colleague Chandu, and the duration of the course is around 36 hours, 36 hours to 40 hours. Yeah. Yeah, I think we have both online as well as classroom trainings. Probably, if you're interested, if you like our demo, probably, always reach us. And if you have any questions, please feel free to reach us, and we are very happy to answer your queries. Yeah, and that's it from our side. I hope you enjoyed the session, demo, and looking forward to join us and learn Hadoop. So thanks for your time.